One last topic to wrap up chapter 4 that's not explicitly related to the postulates or to operators is the idea of how do we deal with multidimensional integrals. So everything we looked at up to this point has been, we've been considering things in one dimension, just in the x dimension. Most of our particle in a box problems have looked at just the one-dimensional particle in a box. But say we're looking at the three-dimensional particle in a box, right, where we have our wave functions, our functions of x, y, and z, and we looked at this at the end of chapter 3, where we kind of have a wave function that looks similar to the one-dimensional case, but we have sort of a part that goes in each dimension, right? X, Y, and Z, right? And our lengths are A, B, and C, right? So if we wanted to use some of these ideas that we've been talking about in this chapter with the postulates, how do we do this with something with multiple dimensions? For example, say we want to find a probability of a particle in a three-dimensional box, probability of the particle being on the right half of the box. So we did this with the one-dimensional box, and we know what we should expect. We should expect that it's going to be similar, that we should get a 1/2, right? It should be on half of the box one side, half the time, half on the other side. And I'll say right half in x, right? So of the box. Now we need to specify which wave function we're talking about. Let's say it's for the ground state, the lowest energy one, where all the quantum numbers for each dimension are equal to 1. We could do this for any of the particular eigenfunctions that we want to. So when we say right half the box, we need to define what we mean. So x from a over 2 to a, and that would leave for y, we're going to go over the whole range from 0 to b, and from z as well will also be over the whole range 0 to c. So if we want to do this problem, what we need is we need an integral, right? We need to integrate. So our definition is integrate over all space over the probability distribution, psi star psi. And I should say not all space, but just over the part we care about, right? So I'll put here our limits are the right half of the box. And then over the relevant variables. So I'll explicitly write them out here. It's over x, y, and z, dx, dy, dz. So how do we do this? Well, we have to integrate over all three variables. So what we're going to have is an integral from a over 2 to a in the x dimension, and we can write this in a way to keep the variable straight. So that'll be for dx. We'll write our dx part of our integral over on the left-hand side just to keep straight which variables are integrated over which, which limits. And we'll have 0 to b for dy, and that indicates our range for y, and 0 to c for dz. And then we have our wave function psi star psi. And so we're just going to end up with since they're not complex, we just end up with everything squared. So I have square root of a over 8bc, our normalization constant. That'll be squared. And then we'll have sine squared nx. Well, nx is equal to 1. So we'll just have pi x over a, sine squared pi y over b, sine squared pi z over c. And this is our integral. Now, the constants will just come out, right? This constants here, this will just come out in front of the entire integral. But how do we handle the rest of this? And what we do is we'll take the x part, and let me do this in colors here. So the x part, we'll look at just the x part by itself. The y part, we can separate all these out into their separate integrals. We'll integrate each of these and then multiply them all together. That's the way this will work. And so we can separate these out into their own specific parts. So we'll have, I'll keep the color coding here. So we have our 8 over abc, that'll be our constants out in front. And then we'll have our x part, which I'll write in red, integral from a over 2 to a, sine squared pi x over a, dx. Integral from 0 to b, sine squared pi y over b dy, and then our integral from 0 to c sine squared pi z over c dz. And each of these parts we can just evaluate separately. Now, I won't go through, in the notes, the lecture notes that are posted online, I go through each of these integrals by themselves, but we've seen these similar integrals already. I'll just, in the interest of time, just give you the results for each of these. So the result of integral number 1 is that we get a over 4. And that's not a 9, that's an a. The result of integral number 2 is that we'll get b over 2. And the result of integral number 3 is we'll get c over 2. So if we go ahead and multiply all this out, our final result is that we'll have our constants, we can't forget about those, 8 over abc, times a over 4 times b over 2 times c over 2. All right, so all the abc cancels, and we'll get 4 times 2 is 8, those cancel, and overall we get 1/2, which is the answer we expected at the beginning. And so again, I skipped the actual solving of each individual part of the integrals, but we've already seen that, right? If you need a refresher, you can go back and look at the examples from chapter 3. But just wanted to go over how do we approach something where we have these multiple dimensions that we're dealing with, and the idea is just to break it up into the separate parts and deal with each of those parts individually. So it's a theme that we've seen in this class. So now you can apply the postulates that we've talked about today to multidimensional problems, and we'll have plenty of that in the future. Don't worry.